The perfect bath is a pretty subjective idea, but there seems to be consensus online that getting the temperature is key. One of the top videos about perfect baths online actually gives a pretty funny description.
Not too hot, but you want it warm, but you don't want it too hot because if it's too hot, you're just burning your skin off.
Now, a bath is drawn by adding a hot volume of water and a cold volume of water, but in a typical bath, the hot water comes out at a constant temperature and the cold water comes out at a constant temperature. And so these two need to be blended together some way to get to that target temperature.
So what is the perfect temperature? Well, the good folks at Birdie put a number to it, 107 degrees Fahrenheit, or 42 degrees Celsius.
Okay, so we have our target temperature, but we want to choose our pampering according to Secret Spa. Sometimes people like to add Epsom salts, essential oils, and possibly bubbles for a bubble bath. This leads us to two questions. If we have two fixed values for temperatures of our hot and our cold water, how do we combine those values into the target temperature that we need for our bath? Secondly, do these percentages change if we add Epsom salts? All right, in this example with pure water, we're gonna go 1 cup of hot water to 1/2 cup of cold water. And to have a little fun with this, let's go ahead and add a little bit of food coloring to make it obvious which one's cold and which one's not. Just stir that up. Okay, so we've got our cold water right here, represented by blue. Excellent. And that cold water has a temperature coming in at whatever that dial says, which we'll look at when we analyze our results. Okay, that should have stabilized. Okay, let's go grab our hot water here. Get our hot cup. Let's go ahead and get that red in there. So cool to just see the drop go. Okay, let's go ahead and if I can get this, stir this up a little bit. Get that nice and red. Great. And the temperature reading on that. Okay. Hopefully that's stabilized. Perfect. And dump in our cold. 1/2 cup. And then a full cup of hot. Okay, get kind of a deep purple and some sort of a temperature result that we will analyze in our graphs. Perfect. All right, that was pure water. Now moving on to salt water.
Pop quiz, when blue and red mix, what color do we produce?
If you're new here, I'm Cody, and I make videos about science, technology, engineering, and mathematics. But I like to go a little bit further than the demonstration alone, and actually show you the data, and talk about some of the scientific equations that have come up that describe and predict how that data looks. If this sounds like something you're into, make sure to hit that subscribe button. Now, back to our experiments. We are at 45.22 grams of salt. Back for our final experiment, we're going to do 1 cup hot water, 1/2 cup cold water with 45 grams of salt in the hot water. All right, let's start with some initial temperatures. Okay, so we've got our cold water right here, and we're clocking in at a temperature of about 74 degrees or so Fahrenheit. Quite. Pretty close. So I'll cheat just a little bit. See if we can top that off. Perfect. Okay. And initial temperature, which is 165 degrees Fahrenheit. Let's add in our 45 grams of Epsom salts. They smell great. Are you feeling relaxed? I am. Okay. Very nice. So we want to try to get that dissolved into the hot water before we dump it and mix it into the combined solution. So I'd like to see the little crystals go away. One more temperature reading. Let's see where we're clocking in at. So now we're at 146 degrees Fahrenheit. So combine half a cup, full cup. All right, and let's get that final temperature reading. Smells so good. Okay, I'm seeing 190.5, 190.3, about 119. Okay, there we go.
Here are the results from our first set of experiments. The red bars show the hot water temperature and the blue shows the cold water temperature. The orange diamond markers show the mixed temperatures. Do you notice any correspondence of ratios of volumes to the mixed temperatures? The first law of thermodynamics states that energy is conserved. If we make the following assumptions, we can write down the energy balance equation, where the T variables are temperatures, the V variables are volumes, the rho variables are water density, and the C little p values are the specific heats for the water. Here is our initial graph, but now I've added the predicted temperature coming from our equation we just wrote down. We see a pretty good agreement between the predicted and observed final mixed temperatures. But if we look back at the thermal video of our experiments, we can clearly see that heat loss is occurring in the hot container and the mixed container, indicated by the bright orange coloring. So I decided to run another set of experiments where I tried to have the same initial temperatures, same volumes, and same salt mass per experiment, 60 grams per cup. And now we see the predicted temperatures are slightly higher than the observed temperatures. This is what we should expect since we see some heat loss. Another curiosity is that the salt mass didn't seem to have any appreciable effect on our temperature mixing. This leads us to being able to simplify our equation by adjusting our assumptions, and we arrive at an equation that relates volumes and initial temperatures to final temperature. Here V1 is the initial cold temperature and V2 is the initial hot temperature, and the same for T little I1 and T little I2. So how does our approximate equation look? The predicted mixed temperature from our simple equation is quite close to the original prediction and observed mixed temperature. Definitely good enough for our bath. Speaking of our bath, how do we use this to get to our target temperature? First, we will approximate the bath as a rectangular 3D object that has some level we will fill to with our water, our final water height, h. Next, we use the volume equation and see that for a fixed area, the volume is proportional to height h, and the total volume is the sum of the volume of the hot water and the cold water. Using this, we can rework our simplified equation to find the height of the hot water when starting with an empty bathtub. Then, just fill the remainder with cold water until the final water height h is reached. After some mixing, the final temperature should be the target temperature plus or minus a degree or two.
All right, let's bring this home. If the average bath is 60 inches by 32 inches by 18 inches, then we can approximate by 56 inches by 28 inches by 18 inches. And if we assume that the average hot temperature is 115 degrees and the average cold temperature is 70 degrees, and going back to our Birdie webpage, the target temperature is 107 degrees, all Fahrenheit, then our volume ratio of hot water to total water is 0.82. Because of heat loss, let's go ahead and bump that up to 0.85. Call it our fudge factor. Lastly, let's go ahead and assume 1 foot in water height of total height of water. That way when we get into the tub, it doesn't accidentally overflow onto the floor. So, to achieve the target temperature, we start with an empty bath and we'll fill up with hot water only up to about 10 inches or a little bit over, 10.2. And then the remainder, we turn off the hot water and we turn on the cold water and fill up to that 12-inch level. After some mixing, the target temperature should be right around 107 degrees Fahrenheit, as predicted by our equations and our experiments. Then all you have to do is add some Epsom salts, stir it up a little bit more, and you're ready to enjoy your perfect bath. Thanks for watching, and if you enjoyed the video, make sure to give it that like and hit the subscribe button for more content like this.